Good morning. Welcome to TMMS Productions, ICSE Physics for Class 10. Today our topic is calorimetry, which is the branch of physics dealing with the study of measurement of heat energy. And we shall now review the chapter. Let us look at it point-wise now. Point number 1. Heat energy is the total internal energy of all the molecules of a body. Point number 2. It flows from a body at a higher temperature to the body at a lower temperature. Number 3. SI unit is joule, that is denoted by J. Number 4. Common unit, calorie, and 1 calorie is equal to 4.186 joule, which is approximately 4.2 joules, and this is important for our conversion factor. We need to know even the definition of 1 calorie. 1 calorie is the amount of heat required to raise the temperature of 1 kg of pure water from 14.5 degrees C to 15.5 degrees C. Now, these definitions you'll find in any textbook. Let's move on. You have to know them by heart. Number 5, temperature. It is the average kinetic energy of the molecules of the body. It's also the degree of hotness. We come to the unit of temperature. Unit of temperature is Kelvin, which is denoted by capital K. Number 7, the quantity of heat absorbed by a substance to raise its temperature is Q equal to mc delta T. You will need this formula for solving the numericals. You need to know this by heart. Then we come to difference between heat and temperature. This is one question that you need to prepare. You can find this in any textbook. Come to number 9. Heat capacity or thermal capacity. It is the amount of heat required by the body to raise its temperature by 1 Kelvin or 1 degree C, and the formula for that is C dash, which is capital C, is equal to M into C. M is the mass, C is the specific heat capacity. It is the same M into C that we used in amount of heat required to raise the temperature of it. So remember, your amount of heat absorbed by a body to raise its temperature is also M into C, means what? It is the heat capacity multiplied by delta T. So we could also write over here, which is equal to C dash delta T. So this gives you another variation for the formula which you can use for our numericals. Now, C dash is M into C. SI unit will be joule per Kelvin, that is J per K. And then we come to the specific heat capacity. Now, specific heat capacity of a body is the amount of heat required by the unit mass of the body to raise the temperature by 1 degree C. The formula being C equal to Q upon M delta T, which you can actually derive from this once you know this formula. Q is equal to MC delta T. C we keep here, M delta T goes that side, so it becomes Q upon M delta T. So we know how to get this relation. Now SI unit, looking at this, it will be joule divided by kilogram and divided by Kelvin. So our SI unit is joule per kilogram per Kelvin. It is joule per kg per Kelvin or joule per kg per degree C. Number 11. Difference between heat capacity and specific heat capacity. You need to prepare this also because this is an objective question that can be asked. Number 12, calorimeter. Learn the diagram, the function of different parts. Why is it made of copper? Why is it placed inside the wooden jacket? What is the function of the insulated material that is kept between the calorimeter and the jacket? How is the heat loss prevented by 3 ways? Which are the 3 ways? Conduction, convection and radiation. You need to know that by heart. 13. Principle of Calorimetry. heat lost by hot body is equal to heat gained by cold body. And so if we have the hotter body which is at higher temperature, its heat lost, if it is M1 C1 delta T1, then it will be equal to the heat gained by the cold body, which is M2 C2 delta T2. We will see this when we are going to solve our numericals. Number 14. Number 14 are going to be all the give reasons. Now the give reasons will be dependent upon the high acidity of water. Now you know that acidity of water, that is specific heat capacity of water, is 4.2 joule per gram per Kelvin, or in SI unit it will be 4200 joule per kg per Kelvin. And so that brings us to number 14, which is give reasons. So the type of questions here will be based on the high acidity of water. Now acidity of water, that is specific heat capacity of water, is 4200 joule per kg per Kelvin, or in CGS it will be 4.2 joule per gram per Kelvin. And so based on this you'll have a few ICSE questions like this which have been asked earlier. Number 1 is climate near the seashore is moderate. Here you compare the high acidity of water with the acidity of water in the sea compared with the acidity of land. And then we have to say that the acidity of water being very high, that is 4200 joule per kg per Kelvin, and hence each kg, I have written this phrase over here, so we'll have to keep repeating this phrase in each give reason. So each kg of water will absorb 4200 joule of heat energy to raise its temperature by 1 degree C or Kelvin. And so it takes a large amount of heat to raise its temperature by 1 degree C. So heating or raising the temperature of the water is very slow compared to the same thing for the land. Okay, and then when it comes to the lowering of the temperature, that means at night each kg of water gives out 4200 joules of heat energy to lower its temperature by 1 degree C or Kelvin, and so the fall in temperature is very slow. Okay, so that is going to give rise to our land breeze and sea breeze, which you'll explain in your own words. The key words are what I mentioned over here. These ones are the key words. This is what you have to remember. Now if you come to the second one, the B part, hot water bottles are used for fermentation. Here again you will mention the same thing. Water has very high acidity, that is 4200 joule per kg per Kelvin, and hence each kg of water is going to give out 4200 joules, which is a lot of energy to lower its temperature by 1 degree C. So this heat will be given to the aching muscles, the body parts, and they will be relaxing and you will get relief from the pain. So now let us come to the next one. Water is used as a coolant. Now where is the coolant used? The coolant will be used to lower the temperature of the heated machine parts. So again we will talk about the same keywords. What will we say? Water has very high acidity. How much it is? 4200 joule per kg per Kelvin. Hence each kg of water is going to absorb 4200 joules of heat energy from the heated machine parts. And it is going to lower its temperature. What? The heated machine parts are going to lower the temperature and the water is going to have its temperature rising. And so we have to talk about it. We have to say that hence it lowers the temperature of the heated machine parts in order to raise its own temperature by 1 degree C. And so it causes a considerable fall in temperature of the heated machine parts. Now we come to the next one. Farmers water their fields during severe winter. Where there is frost predicted, they will water the fields at night. Now the temperature is lowered at night, which means the fields can lower the temperature below the freezing point of water. So we want to avoid the freezing of the crops. And so we start the sentence exactly the same way. Water has very high specific heat capacity, that is 4200 joule per kg per Kelvin. Hence, each kg of water here will give out 4200 joules of heat energy to lower its temperature by 1 degree C or Kelvin. And this heat is given to the crops in the field. And so the prevention of freezing of the crops takes place. Living beings have high water content in their bodies. Now remember, again, high water content is going to be linked with the high SHC of water. That is, water has very high specific heat capacity. How much? 4200 joule per kg per Kelvin. And so during the summers, the water, each kg of water has to absorb how much? 4200 joules of heat energy to raise its temperature by 1 degree C or Kelvin. And so the temperature of the body, the living body, does not rise too fast. Now, in winter, what happens? In the colder climate, each kg of water gives out 4200 joules of heat energy to lower its temperature by 1 degree C or Kelvin. And so the fall in temperature of water also is going to be very slow. So it's going to avoid the freezing of the body. 15th, give reasons based on heat capacity. Now here your questions will be based on mass. So you have to look for whether there is more mass. More mass means more heat capacity. Less mass means less heat capacity. Why? Because our heat capacity C dash is equal to M into C, and it depends upon the mass. So look at the ICSE questions here. Calorimeter is made of thin sheet of copper. So what we have to say? Thin sheet of copper means it decreases the mass, decreases the heat capacity, and so the calorimeter will have negligible amount of heat absorbed by it from the contents to acquire the temperature of the contents. We come to the second one. Second one is base of an electric press is made thick. Now what do we say? The thick base increases the mass, so it increases the heat capacity, and so it takes more amount of heat to raise its temperature by 1 degree C, as well as it liberates more amount of heat to lower its temperature by 1 degree C, and so it remains hotter for a longer time. Number 3, cooking vessels have thicker base. Again we say thicker base means what? Has more mass, and therefore it will provide a lot of heat without much rise in its temperature. Number 16, change of state and latent heat. Now in this particular point we will be talking about latent heat of fusion. So namely we'll talk about latent heat of fusion of ice and latent heat of vaporization. So it becomes latent heat of vaporization of steam. Then we come to specific latent heat of fusion and specific latent heat of vaporization. Now all these definitions you have to know by heart and you have to apply them. So since it is a learning topic, I am not going to go through this as such because it's only a review. Only thing is that when we talk about these two, latent heat of fusion and specific latent heat of fusion, what is the difference? Specific latent heat of fusion is when we talk about unit mass. And when we talk about specific latent heat of vaporization, how is it different from this point? Here we talk about the unit mass and here it will be the given mass. So now let us come to the next part, which is the graphical representation, the heating curve. The heating curve, and also you have to learn the cooling curve. I have shown you only the heating curve. As you can see that on x-axis we have energy, and on y-axis you can see temperature, and we have shown this is point O, which is showing minus 10 degrees C, because this is representing temperature in degrees C. And of course the graph is not according to the scale, it is just a representative diagram. So this is minus 10 degrees C, this is 0 degrees C, this is 100 degrees C, and this is 110 degrees C. And so you will see that for the given mass of ice at minus 10, when we supply heat, it will show the rise in temperature, and then at point A is where the ice will start melting, and that starts at 0 degrees C. And at 0 degrees C, the melting begins, and at B, melting finishes. So AB represents melting, and BC represents the rise in the temperature of water, because now it has formed water here. This is from B to C, it is showing water. This is rise in temperature till the water becomes from 0 degrees C to 100 degrees C. Then C to D, you will see that here the vaporization begins and here vaporization ends. And so here the temperature is going to be constant, and the steam will be formed at point D. So D to E will be rise in temperature of the steam. Now the change of state is where the temperature remains constant. So you will see from the graph, you can find the melting point of the substance and the boiling point of the substance, like so. And also understand that this AB is where the potential energy increases when heat energy is supplied. So the kinetic energy remains constant, but potential energy increases. Now, between C and D, where we have a liquid becoming a vapor, and so the intermolecular bonds are totally broken off, and so the potential energy increases to a large extent, and so from C to D you will see a large amount of energy is required. And so the part of the graph CD, which is representing the latent heat of vaporization, is going to be much longer than the part where you see the latent heat of fusion of the solid, where the intermolecular bonds are only loosened. Here the bonds are loosened, here the bonds are broken off. Now you may be given a numerical based on this as well. So in that case, you will be given some numbers here. Then here also some numbers will be given here this side. And here again some number will be given here. So I'm just showing these lines over here like this. Okay, so some number will be given here, some number will be given here, some number will be given here, some number will be given here. And so if they tell you that so much is the energy, then you will use the formula for the rise in temperature of the ice using MC delta T. If you want to find out this particular a region where you can find this energy, and then if the mass or specific latent heat of fusion is to be found out, then you can use the formula over here, Q is equal to MLF. Here again it will be rise in temperature, so the total heat required for that rise in temperature will be this minus this, and that will give you Q equal to MC delta T. Here again it will be the heat energy for the change of state over here, and that will give you Q equal to MLV, that is specific latent heat of vaporization, and here again we'll be using MC delta T. So like that you can use the knowledge that is supplied here and how you have interpreted the graph, and you can solve the numericals based on the graph. Now let us come to the next part, which is number 18. Number 18 talks about effect of pressure on boiling point. Now, the pressure increases, the boiling point also increases. Remember the example of pressure cooker, and also effect of pressure on melting point. If the pressure is increased on certain substances like ice, you know that the melting point of ice is going to be lowered, and you have the give reasons based on that, like the ice skaters do not leave any marks on the ice when they are ice skating, And for this again you will have the give reason like at high altitudes pressure cookers required for cooking. Then we come to point 19, effect of impurity on boiling point and effect of impurity on melting point. Now boiling point, when you add the impurity, the boiling point increases, and so we have like addition of salt to the food increases the boiling point, and so large amount of energy is given to the food in order to cook. So that again is another give reason. The effect of impurity on melting point is where salt is added to the ice, and ice, the melting point of it is lowered, and that is used in making a freezing mixture. Remember the formation of kulfi? Okay, so all those give reasons will be given over there in that. Now we come to number 20. We have the give reasons which are based on latent heat. Here we'll have to make use of the fact that specific latent heat of ice is 336 joule per gram or 336,000 joule per kg, and the specific latent heat of steam is 2268 joule per gram, or it will be 2268000 joule per kg. Now let us see the give reasons based on this. Ponds do not freeze all at once during winter. Now when we write the answer for something like this, we know that during freezing water is going to liberate heat. So you start with ice has very high specific latent heat of fusion, which is 336,000 joule per kg. Hence each kg of water at 0 degrees C is going to liberate or give out 336,000 joules of heat energy in order to become 1 kg of ice at 0 degrees C, and thus it cannot freeze all at once. Let us come to the next one. Next one is drinks get cooled more effectively by adding ice than ice cold water. Here we will take this number over here because we drink small quantity of water, so we will need smaller quantity of ice in it. So we start exactly the same way, saying that ice has very high specific latent heat of fusion, and therefore at 0 degrees C extracts 336 joule of heat energy more than 1 gram of water at 0 degrees C in order to become 1 gram of water at 0 degrees C. Now that phrase is important, and so it will be effectively cooling the drink. So we come to the next one. Even in hot summers, the regions near the Himalayas remain cooler, and the reason for this is Himalaya will have tons and tons of ice over there, and so what will happen? It will have to have more heat required to melt the ice. So we start our sentence with the same thing, that the ice has high specific latent heat of fusion, and we take this number 336,000 joules of heat energy, and so each kg of ice at 0 degrees C will absorb 336,000 joules of heat energy in order to become 1 kg of water at 0 degrees C. And so the heat required to melt that ice is taken from the surrounding, and the temperature drops, and so it becomes cooler. Then we come to the next one. Weather becomes cooler after the hailstones fall, that is after the hailstorm. And for this again we start the same way. We say that ice has very high specific latent heat of fusion, that is 336,000 joule per kg. Therefore each kg of ice in the hailstones will absorb 336,000 joules of heat energy from the surrounding to become 1 kg of water at 0 degrees C. And so the heat absorbed from the surrounding will make the temperature of the surrounding fall. we come to the numericals. That's number 21. The first one over here, find the heat energy required to raise the temperature of 10 kg iron body by 15 degrees C, and we are supplied with specific heat capacity of iron, which is 483 joule per kg per Kelvin. Now we first write the data. Mass is 10 kg, which is supplied here. Specific heat capacity is given here, 483 joule per kg per Kelvin, and the temperature is rising by 15 degrees C, so delta T is how much? 15 degrees C or Kelvin. And so now we use the formula for rising temperature, that is the heat energy Q is equal to M into C into delta T. Substitute the values and then you will see unit wise Kelvin got cancelled, kg got cancelled, and only joule is remaining here. So you have 4830 multiplied by 15, simple calculations, and that is 72450 joules, and that is our answer. Calculate the heat capacity of a Bethel vessel which absorbs 2000 joules heat energy to raise its temperature by 5 degrees C. Now heat capacity is C dash equal to question mark, Q is equal to 2000 joules, and delta T is equal to 5 degrees C or Kelvin. As you can see, this data and this data has been supplied. Now Q is equal to MC delta T, but we already know that C dash is equal to M into C. So we will write it as C dash delta T. And therefore you will have 2000 joules is equal to C dash multiplied by 5 Kelvin. And therefore you will have C dash equal to, this 5 comes the other side, so I'll write 2000 joule divided by 5 Kelvin. So you will see that 5 goes once and here it will go 400 times. So it will become 400 joule per Kelvin, and that is our heat capacity, which is our answer. The next question. A metal body of mass 50 gram at 59 degrees C is dropped into 30 grams of water, and the temperature of the water rises by 15 degrees C. Find the initial temperature of water provided ICSE of metal equals 0.9 joule per gram per Kelvin, ICSE of water equal to 4.2 joule per gram per Kelvin. Now to solve something like this, you need to have a few things clear for not just the metal but also for water. Now for metal, we have been told that the mass is 50 gram and we have been provided with ICSE, which is 0.9 joule per gram per Kelvin, and also we know our T1 is 59 degrees C and T2 we do not know yet. Let's come to water. The mass of water is given to be 30 gram. ICSE is here 4.2 joule per gram per Kelvin. Initial temperature, find the initial temperature, so we'll call it as X. And your T2, that is the final temperature, we know that the initial temperature rises by 15 degrees C. So it becomes X plus 15, and so the temperature of the metal as well will be X plus 15 Kelvin. So now we know that the delta T for water, that is rising temperature, is 15. So we know that for delta T for water is 15 degrees C or Kelvin, but delta T for metal is going to be higher temperature minus the lower temperature. So 59 minus X plus 15. and therefore I will just squeeze in over here. Delta T will be equal to 59 minus X minus 15, which gives us, this is the delta T, that is change in temperature for metal. Now we know that at equilibrium, according to the principle of calorimetry, we will have the heat lost by the metal will be equal to heat gained by water. So we know that the heat is given by the formula mc delta T. So for our metal, we'll call that mc1 delta T becomes m1c1 delta T1, and for water it becomes m2c2 delta T2. For mass of the metal, we can see this. It is 50 into C is 9 upon 10, and our delta T is 44 minus X, and that will be equal to M2 is 30 for water into C2 is 42 upon 10 multiplied by 15. So we shall have 44 minus X equal to 30 into 42 upon 10 into 15, and these two numbers will come here this side. So 10 upon 9, and I will have 50 in the denominator, so I shall write here like so. Cancel the zeros. 3 goes once in this, 3 3 is 9, 3 ones and 3 5s 15, 5 ones and 5 ones. So we will have 44 minus 42 will be equal to X, and therefore your X will be 2 degrees C, and this becomes the initial temperature. Of water. And that is our answer. And now we come to one more question out here. And the question now reads, a vessel of mass 50 grams containing of water is at 30 degrees C. How much ice is needed to cool it to 10 degrees C? Now for something like this, again we will do for our vessel. Mass is equal to 50 gram. SHC for the vessel is 0.4. It is given here. Joule per gram per Kelvin. And its initial temperature T1 is going to be 30 degrees C, and we have to add ice to this so that it becomes at temperature 10 degrees C. So T2 is equal to 10 degrees C, and that will give us delta T for it 30 minus 10, that is 20 degrees C or Kelvin. We now come to vessel containing water. So our next quantity is water. Again, for water, mass is given as 100 grams and SHC for water is 4.2 joule per gram per Kelvin. T1 will be 30 degrees C. T2 also will be 10 degrees C because the vessel and the water, they are in contact with each other, and delta T also will be 20 degrees C or Kelvin. Now let us come to ice. Now for the ice, they are saying how much ice is needed. So the question asked is the mass of the ice, which we'll call as X gram. Now ice is going to be at 0 degrees C, it's going to be melting, and so we have to use the specific latent heat of fusion, that is LF, and that is going to be 336 joule per gram. Now this heat will be used to change its state and is going to become water at 0 degrees C. But the end result is water at 10 degrees C. So we are going to require heat for the change of ice into water, and then water at 0 degrees C to water at 10 degrees C. And so for that we will need MC delta T formula, so we need the SHC as well. So 4.2 joule per gram per Kelvin, and our delta T for water is going to be from 0 degrees water to 10 degrees water, which means it's going to be 10 degrees C or Kelvin. Once we have understood this, we are ready to say that at equilibrium, according to the principle of calorimetry, the heat lost by the vessel plus water is equal to heat gained by ice. And so for vessel we will use M1 C1 delta T1 because it's the change in temperature. For water we will write M2 C2 and delta T1 because both of them are in contact with each other. Your delta T will be the same therefore. For heat gained in ice, ice is first going to melt, so it's going to be mass into latent heat of fusion, plus once it becomes water, it's going to show rise in temperature, so it becomes MC delta T. And so now we substitute the values. M1 C1 delta T1 will be for this. We will use this, this and this. So that will give you 50 into 4 upon 10 into 20 plus. Now we'll take this, this and this. So it becomes is equal to MLF. So we have to find the value of mass. So it is X multiplied by 336 plus x into 42 upon 10, because now it's become water, multiplied by delta T. And now this will give us 5 to 10, so 100 into 4. So that is 400 plus here 42 into 2 is 84. So 8400 is equal to 336x plus 42x. So we will have 378x is equal to 8800, and so we will have x equal to 8800 upon 378, and your x will come out to be 23.28 gram, and this is the mass of ice, and that is our answer. So now you see that you have had practically the whole chapter reviewed, and I hope it has given you enough confidence. I hope you'll be able to solve each and every question that is asked on this chapter, and I want to wish you all the best, and thank you for watching.